Today, we will be presenting a paper called Quality and Complexity Measures for Data Linkage and Deduplication.
This paper was written by Peter Christen and Karl Geuser and published in 2007. It discusses various quality and complexity measures used to assess techniques for data linkage and deduplication. As the name suggests, data linkage is the process of linking records that refer to the same entity across different datasets, and deduplication refers to the removal of records that are duplicated within a dataset. We will first discuss data linkage and deduplication processes and then discuss how these techniques may be evaluated. Finally, we will present the examples provided in the paper.
Data linkage and deduplication can be used to improve data quality and integrity. In the health sector, data linkage helps to deal with survey results and then produce clean information to improve health policies. Business link and deduplicate their data to compile mailing lists. And statistical agencies link census data for analysis. In taxation offices and Department of Social Security, data linkage and deduplication can help to identify people who registered for assistance multiple times, or who is working but also collecting unemployment benefits. Data linkage can also help to quickly access files on a particular individual to prevent crime. In bioinformatics, data linkage can help to match genomes. In web searching and document indexing, copies of same documents can be identified and filtered. Online shopping usually needs to find and compare products from different stores, where product descriptions can be different. There are some difficulties in data linkage process. First, real-world data contains noise, sometimes have missing values or incorrect records. Data from different sources may appear in different formats. For example, names are often reported differently by the same person depending upon the organization they are in contact with, resulting in missing middle names, initials only, or even swapped name parts. To deal with these problems, data are cleaned and standardized before linkage. Second, in linkage of two datasets, the number of possible record pair comparisons equal to the product of size of the two datasets, and therefore can be very large. For example, linking two datasets with 100,000 records each would result in 10 billion record pair comparisons. To reduce the number of comparisons, there are two ways. One is blocking. That is, they use one or a combination of record attributes called the blocking variable to split the data sets into blocks. All records having the same value in the blocking variable will be put into the same block, and only records within the block will be compared. Another way is sorted neighborhood approach, where records are sorted according to the values of the blocking variable, and then a sliding window is moved over the sorted records, and comparisons are performed between the records within the window.
Deterministic techniques involve linking datasets using a unique identifier, a key. However, not all datasets have unique identifiers that can be used for linking, and they may not be of high enough quality. An alternate deterministic technique is to use a set of rules to classify record pairs, though this is quite labor-intensive and usually only done for smaller datasets. Probabilistic linkage techniques are more flexible than deterministic techniques, since they do not rely on common unique identifiers in all datasets. Instead, a set of common attributes are investigated. If the common attributes of a pair of records predominantly agree, then they are classified as matches. If they predominantly disagree, they are classified as non-matches. Finally, there are also techniques the paper refers to as modern approaches, which utilize techniques from other areas such as machine learning. Here I will give a little more detail on probabilistic linkage. Firstly, a ratio of probabilities is calculated, where the numerator is the probability of an agreement pattern given that the record pairs are matched, and the denominator is the probability of an agreement pattern given that the pair is non-matched. Essentially, this means that R will be large if there's high agreement between two records, and R will be low if the agreement between the two records is low. If R is greater than some threshold T upper, then it is classified as a match. If it is less than T upper and greater than a threshold T lower, then it is classified as a possible match. If it is less than T lower, it is non-match. In the case that a record pair is classified as a possible match, it is sent to clerical review, meaning that a human will classify it. This is okay for small datasets, but when the datasets become large, it is no longer possible to classify all possible matches by hand. This is where modern approaches such as supervised learning try to reduce the amount of clerical review needed.
To recap, this is the data linkage process. As mentioned before, data was first cleaned and standardized, and then using blocking to compare. The output of the blocking step are record pairs, and then the pairs are weighted in comparison step. The output of the comparison step are vectors with numerical matching weights. These vectors are then used to classify record pairs into matches, non-matches, and possible matches according to their weight.
For the following quality measures, we assume that the algorithm does not classify possible matches. We consider only one threshold, t, and the pairs are classified as either matches or non-matches. Correctly identified matches and non-matches are true positives and true negatives, while matches and non-matches that are incorrectly classified are false negatives and false positives. Evidently, this confusion matrix can only be applied to a dataset for which the true labels of each pair is known. As you can see in this plot, the vast majority of pairs will be classified correctly as non-matches, so there will be a huge number of true negatives in comparison to true positives, false negatives, or false positives.
The linkage and deduplication are classification problems. Various quality measures are available to the data linkage researcher and the practitioner. First of all, we can use the 5 measurements on the left slides: accuracy, specificity, false positive rate, ROC curve, and AUC. They all include the number of true negative and are affected by the large number when used in the comparison space. True negative will dominate the formula, and the value of those measurements will be too high. Thus, those measurements will not be a good quality measures for data linkage or deduplication and should not be used. Next, we can focus on the right part of our slides. Those measurements are all exclude the true negative value, and they are all widely used in practice. For example, the precision equals to true positive divided by true positive plus false positive, and recall equals to true positive divided by true positive plus false negative. In addition, there are some recent publications that advocate the use of precision recall graph over the use of single number measures, like accuracy or maximum information. Also grants that such single number measures assume that an optimal threshold value has been found, which is not real in the practice. While all quality measures presented so far assume a binary classification without a clerical review, a new measure has been proposed recently, the PP value. The low PP value are desirable as they correspond to less manual clerical review. An assumption in the analysis and discussion of quality measures given so far has been that all record pairs are compared, which is computationally feasible only for small datasets. In practice, blocking can be used to reduce the complexity of algorithms. Those techniques aim at cheaply removing as many record pairs as possible from the set of non-matches without removing any pairs from the matches. It uses one or combination of record attributes to split the dataset into blocks. All records having the same value in the blocking variable will be put into the same block, and only records within a block will be paired. There are 2 complexity measures that quantify the efficiency and quality of such blocking methods. The first is reduction ratio. Reduction ratio equals to 1 minus MB divided by the full comparison space, and MB is a number of record pairs produced by the blocking algorithm. The second is pairs completeness. It is measured by the number of correctly classified truly matched record pairs divided by the total number of true matches. Pairs completeness is very similar to recall. Actually, there is a trade-off between those 2 measures. In other words, between number of removed pairs and the number of missed true matches. Next, we will use a real-world example to show how blocking works in practice.
Now we can see the real-world example about how the blocking works in practice. This dataset is the New South Wales Midwives Data Collection, MDC. There are 175,211 records in this dataset, and the task is to deduplicate the dataset. If we don't utilize blocking, the full comparison space for those records would result in 175,211 multiply 175,210 divided by 2. And the result is the crazy number shown on the slide. This may cost too much time for computer and cannot be accepted in practice. After using standard blocking, we only got 759,773 record pair comparisons. So the RR value can generate the equation in the slide. Actually, the total number of truly classified matches was 8,841, and with 8,808 truly matches after blocking, so the PC value equals to 8,808 divided by 8,841, which equals to 0.99626, which corresponds to more than 99.6% of all true duplicates being included in the blocked comparison space. More specifically, we can see some different quality measures comparisons between the full comparison space and the blocked comparison space. In the plot, the dotted line represents full comparison space and the solid line represents the blocked comparison space. The first three measures, accuracy, specificity, and false positive rate, all have different shapes of graphs between two spaces. A large number of Tn compared to the number of Tp resulted in the specificity measure being very similar to the accuracy measure. For the precision recall graph, it does not change at all, while change in the F measure graph is only slight. Interestingly, being promoted as robust with regard to skills classification problem resulted in the least illustrative graph, especially for the full comparison space, making it not very useful for data linkage and deduplication.
The paper gives several recommendations for how best to assess the quality of a data linkage technique. Firstly, to compare techniques, they must be applied to the same dataset, since their quality will depend on the nature of the data. A variety of datasets should be collected and made publicly available so that techniques can be compared using the same datasets. It is recommended that quality measures should be calculated for several datasets and an average quality should be reported. Secondly, any quality measures that contain the number of true negatives should not be used, since this distorts the result. On the other hand, precision versus recall and F-measure graphs are recommended. Thirdly, since blocking may remove true matches, and this depends on the blocking method or parameters, quality measures should be reported without blocking if at all possible. If this is not possible, the blocking parameters and procedures should be published to make the experiment repeatable. Finally, Christian and Geuser recommend that the order of complexity of the technique should also be published, as this is an important aspect of choosing a data linkage technique.
In order to cooperate well with each other, we had 3 meetings. First meeting, decide on paper dividing, then work on slides independently. Second meeting, check the slides and scripts for each other. Confirm time division. Record videos separately. Third meeting, combine the videos together. Our division of workload is reasonable, where Swanti is responsible for introduction, explanation of techniques and conclusion, Mei Chen for applications, difficulties, and solutions. Xin talked about different quality measures for data linkage, and Shu talked about a real-world blocking example.
This is the end of our presentation. Thanks for your attention.